Okay. Hello, everybody. Moya. Good afternoon. Do you hear us? Yes. Yo. Good. Okay, let's wait for 1 minute to make sure that the participants joined us. Hello, Moya. Okay, so good afternoon and welcome to today's webinar in Neural Network, the brain behind intelligent system. So as we have seen last week that machine learning has gained has been explained by our speaker. I hope that you will discover the difference between why we use machine learning, and in particular sometimes we need deep learning, and this is the objective of this topic of today. Deep learning and neural network tend to attract more attention and interest than many of the other topic. So let's discover this topic with our speaker of today. So our speaker is Dr. Shiwi Liu. He is a Royal Society Newton International Fellow at the University of Oxford. He previously served as a postdoctoral fellow at the University of Texas at Austin. He obtained his PhD with the cum laude from Eindhoven University of Technology in 2022. His research focused on leveraging understanding and expanding the role of sparsity and low-rank approximation in neural network, whose impact span many important topics such as efficient training, inference, transfer of large foundation models, robustness and trustworthiness, and generative AI. He received two Rising Star Award from COST and the Conference in Parsimony and Learning. His PhD thesis received the 2023 Best Dissertation Award from Informatic Europe. So we are happy to have our speaker with us today. Thank you so much for being with us, and thank you for your dedication time to prepare the presentation. I will give you the floor to start the presentation. Thank you.
Thank you. Thank you for the great introduction. And I'm honored to give this presentation about neural networks, the brain behind intelligent systems. So here is today's agenda. I will go from difference of machine learning and deep learning to several basic type of neural networks, like multi-perceptual neural networks, recurrent neural networks, convolutional neural networks. And finally, I will briefly discuss the fundamental architecture behind the ChatGPT chatbox, which is transformer, and how it is built at trained, and how can we use it to improve our life efficiency, something like that. And I think based on the introduction, I think you have be introduced the machine learning and how machine learning helps to help our daily life. And if you must be curious what is difference about this famous machine learning and deep learning. And at the beginning, I would say both of them belongs to a big concept of artificial intelligence. So artificial intelligence is something like a concept. The goal of artificial intelligence is to teach or to build machines, teach machines to approach or exceed the behavior or reasoning ability of AI. And deep learning is one subfield of machine learning. And compared to traditional machine learning, like traditional machine learning usually design different features by human beings, or is handcrafted features, and you use these features to do classification. And in contrast, deep learning do all these features by automatically. So we don't have to design different features according to different input by ourselves. Instead, we use our model to learn it by itself. And there are several differences between machine learning and deep learning. So the first is data dependency. So when learning data is small, machine learning algorithms usually outperform deep learning, because deep learning is much more data hungry. You have to use a bunch of, like, for example, current ChatGPT or chatbox. People complain they almost learn all the data on the planet. So if you have small data, you use machine learning. If you have many data, you use deep learning. And hardware dependency is the second concept. And machine learning usually don't require massive hardware like GPU provided by NVIDIA, but deep learning usually are heavily depends on the very fast and elegant computing resources like GPU or TPU. And machine learning, a deep learning algorithm usually need to longer time to train, because there are so many parameters, and it can be something like up to trillions of parameters. And interpretability is another issue of deep learning. So deep learning is inherently difficult to understand, because they learn the model learn the feature by itself. It's not designed by our human being, so it's very difficult to understand, to interpret deep learning. In contrast, machine learning has better interpretability, so it's more reliable. And applications is deep learning techniques are more suitable on structured data, like tabular data or sequence data. On the other hand, deep learning are more suitable for large scale data sets, like network corpus, internet corpus, images, something. And the one basic the fundamental components of deep learning is neural networks. And neural networks is inspired by biological neural networks. As we can see on top is something, the neural networks in human being. So we have different neurons, and different neurons are connected with the with the what's the word of that?
Snaps.
Snaps. Yes, exactly. And on the bottom is artificial neural networks, which simulate the architecture of biological, like human brains. It contains input layer, hidden layers, and goes to output layers. And the neurons in neural networks are connected with weights. And let's look deeper into the architecture of neural networks. So what is neural networks essentially? A neural network is a computational model inspired by the human brain, designed to recognize patterns to solve complex problems. So it consists of interconnected artificial neurons that process data in layers. So what is artificial neurons here? So an artificial neurons is a fundamental unit in a neural networks inspired by human brain. So it processes input, apply weights associated to each input. And after you calculate the neural output, you also apply an activation function to slightly change the output. Why we do that? Because we want use activation functions. We usually can transfer, because this input times weight is a linear transformation. With some nonlinear activation, we can increase the capacity or capacity or representation ability of your function to simulink every different types of function. And let's here looking a little bit deeper into the neural networks with some function. Assuming here we have one hidden layer neural networks, and X is the input. And here are 4 neurons. Each one is called U1 to U4 with 4 hidden units. And next layer is our output layer. And Y is our output equals to U2. And first we need to, for example, given input X with the Xi to Xd, we need to calculate the first hidden layers U. And here, before we calculate the output of U, we first calculate the Z1 equals to weight metric W, here different weight metric, times to X, and plus the bias. So the bias is a scalar for each unit. And after we calculate the Z, we apply a nonlinear or linear activation function sigma on top of Z. So by doing this, that we can calculate the output the values of neural U here. So we can have four value of output neural. And after we calculate the first layer, we need to calculate the last layer or the output layer, which is U. So we do the similar things as the first layer. We use the different weight metric W2 times the output of first layer will be the input of the next layer. So our input here is XU, and we calculate this linear transformation and apply another nonlinear activation here. So we will have, after this calculation, we will have the output U2, which is essentially our output. This is how the feed-forward operation of one hidden layer neural networks. And there another important component of neural networks is activation function. So activation function is mathematical function applied to output of a neural to introduce nonlinearity into neural networks. This allows the network to learn complex patterns and make accurate prediction. So there are many types of activation functions. Most famous one is linear units and ReLU, rectified linear units, and sigmoid, also tangent. I will briefly mention each of them. So linear units is something mapping your input linear to your output. So this actually doesn't give you any non-linearity, but sometimes in some cases people use that. What is more common used is this one, ReLU, rectified linear units. So when X is larger than 0 is basically a linear unit, but when X is smaller than 0, it becomes 0. So this activation function is most famous one in modern neural networks. It's not differentiable at when X equals to 0, but still performs well in practice. And its gradients is very easy to calculate. When X is larger than 0, the gradient equals to 1. When X smaller than 0, the gradient equals to 0. And there are other versions of ReLU, like for example, leaky ReLU or GALU. There's so many versions of the ReLU, and most of them are trying to, because if we use a traditional original ReLU, it doesn't have gradients when X is smaller than 0, which is not very informative. So in order to encourage more healthy or informative gradients, people just modify ReLU into different variants. Just make sure when x is smaller than 1 and so smaller than 0, they still have a non-zero gradients. And there are other sigmoid activation functions and tangent, which are usually used in recurrent neural networks. And another very important why neural networks become so popular after 19th, because of the invention of backpropagation. Why we need the backpropagation? Because the function, remember the goal of training neural networks um, is to minimize your loss function, which is used to calculate how far our model is close to our target objective. If the loss function is we minimize is to 0, which means our model can perfectly fit the data to achieve our objective. Now, how can we minimize our loss function? The way in deep neural networks is we use gradient descent, trying to update the weights to minimize their loss function. So how can we do the one essential part of gradient descent is we need to calculate the gradients of the weights. So the most basic operation is gradient chain rule, is the technique we use to calculate gradients. For example, if we have a univariant function fu and u is a function of v, like here, the gradient chain of rule is the derivation is of x to v equals to derivation of f to u and derivation of u to v. So this is called the gradient rules, chain rules, which is the most essential mechanisms of modern deep neural networks. And this in the common implementation like PyTorch is already they achieve automated gradients, so you don't have to calculate by yourself. It's once you create your model in PyTorch, it calculated by it take care of it for you. And here's a concrete example of a gradient chain rule of a logistic regression model. For example, if we have input x and we have a linear layer z and our output after apply a sigma activation. And loss function is can be a square root. It can be any kind of loss function. So we first calculate, because our goal is to calculate the gradients of a derivative of a loss function to our weights. For example, bias or w. Here's the loss function. We essentially want to calculate these two things, and we can do the similar thing as before to calculate their gradients. So once we get their gradients, we need to use optimizers, for example, stochastic gradients, or add them to update our weights. Yeah, this is a basic what is called backpropagation, which is based on gradient chain rules. And we need, after we get gradients, we use our optimizer to update our weights. And before we talk about some very simple one hidden layer neural networks, and usually why we call it deep neural networks, because it has many layers. So this can be called that deep. Now, for example, the ChatGPT or DeepSeek model, it can has hundreds of layers instead of just 1 or 3 layers. So here are the 6 stages to train or to build our neural networks and to train our neural networks. So first, we need to initialize weights of our architecture, which is W and bias B. After we initialize the weights, we can perform one step forward propagation. For example, we give our model X here, and we calculate the hidden units layer by layer until we get the final output. So once we get the final output, we can use the output to calculate the error function with our label. This tells us how far our model is from our targets. And then we perform backpropagation to calculate the gradients to do the grid updates. So this is one step of your training. From step 2 to step 5 is usually called one step. After you calculate your after you update your weights, you redo the forward propagation with your new weights. Then you have a new error function. You will know at this step how far you is from your target. Then you recalculate the gradients, updates the weights accordingly. So this happens. This training usually involves thousands of hundreds of thousands iteration of steps. Then you can probably, let's say this is your launch landscape. At the beginning, you're at this point, and then you, with one step, you probably you jump from this point to this point, then you jump to this point until the end of the training. You can convert to this what we call local minima, which has lowest loss ever possible to your label. Okay, I think I have 25 minutes more, and this is called the previous neural network is called so-called feed forward network. So it's just we just stack different a couple of layers by layers until we get our output. So the drawback limitation of feed-forward neural network is different. Your output of your different input is actually has no interaction. So for example, your current output has no dependency on your previous image. For example, this time you can predict to a dog. Once you feed a cat image to your model, it will gives you a cat. So there's no time dependency or data dependency between your different data. But when we deal with the data that has time dependency or distance dependency, for example, your text input or time series data, which like you feed essentially instead of feed the image in your network, you feed the different text of your textbook. So the text is different from image. Text usually are highly dependent on your closed data and closed text. Like for example, recurrent neural networks, they have their own relationship between each other. And in this case, the feed-forward neural network cannot capture the dependency between your data. This is why the current neural networks are introduced. So instead of feed your output directly to your next of this layer directly to your next layer, you feed different time step of your data recursively into the same layer. So as this diagram shows, the output of this layer will become the input of this layer. So you recursively feed your data into the same layer. Then you feed the output of the next layer. So recurrent neural network the benefits of recurrent neural networks can capture the dependency between different data sample, which is essential for time series data or text data. This is why before transformer or before the invention of transformer, recurrent neural networks dominates the fields like language modeling, text generation, speech recognition, because they are time series data. And however, if your input data is image, Like if it's only one image, you don't need to use recurrent neural network. What is more popular is convolutional neural networks. And why convolutional neural network is better? Because one, if your goal is trying to capture some small texture in your image, you convolutional neural network is position in how it's called invariant, position invariance, and rotation invariant, and it doesn't require any dependence of your data. And one benefits of convolutional neural network is very parameter efficient. Actually, you share the same parameter across the whole input. This is an example of how convolutional neural network works. So first we convert this, let's say this image, into some RGB number, which can be recognized by your computer. Then you apply this convolutional kernel, which is square, usually a square of parameters with different values, and you apply this kernel step by step. First, let's say your first calculation is you apply this kernel into this 9 pixels, then you get this 3. Then you apply the same filter or kernel into your next part of your input, this part. Then you get this output -1. So you do this, you perform this convolutional operation across your input, like this way. Then you get your new output, which is also an image. And you perform max pooling. Max pooling is something like, for example, given this 4 pixel, you calculate the maximum values of this 4 pixel. Then you get this output. So this output essentially is also a picture. So what convolutional neural networks do is, given an image, you perform convolutional operation across different. Let's say these are their RGB sub picture. You perform convolutional you perform convolutional operation, you can get a new image. And then by doing this, you're actually extracting some different level of your features from your original input. And this features is number of features is determined by you. You can determine how many features I want to learn from this single input, and you just use different features to make your prediction. And here is the example diagram of convolutional operation. So you apply your kernel, which is your weights on this part of your picture, and you operate across your image. Then you can get a new picture, which we call feature. And after you get a bunch of features like here, you will follow by several layers of feed-forward layer, just like what we call MLP or feed-forward layer. You can make your prediction. If it's dog or cat, boat or bird, it's based on statistics. The class with the highest label will be your final prediction. For example, here both boat and birds have equal prediction number. Usually they don't have equal one. You will choose the one with the largest probability. And since 2017, so before 2017, for image data, we use convolutional neural networks. For time series data, we use recurrent neural networks. However, everything changes after 2017, which because of one paper, which is called "Attention is All You Need." This paper actually introduced the transformer architecture, which is now dominates everything in deep neural networks. So there's a joke about the paper. So the original title is "Attention is All You Need," and now we figured out attention is all you need to raise billions for your AI stuff. Why is this case? Because all the authors, they were in Google, but after the paper get popular, the architecture get popular, they all left Google to build their own startups. And these are actually the top tier AI startups, AI companies, which we usually use like ChatGPT or Cohere or Cloud from Anthropic. They are all from this paper originally. And with the chat box or current AI LM, so we can do a lot of things. For example, we can ask chat box to answer our questions, to summarize the main idea behind the articles. And I believe everyone has used ChatGPT to help you to finish some work more efficiently. And also, we can use transformers to help us generate pictures or videos, like OpenAI's DALL-E. Or it's what is more mature is, I think, this chatbox is so good at coding. Even as a computer scientist, I cannot say I can beat ChatGPT. They can easily beat me in terms of coding. And why this? What's the booster behind the success of large language models or large foundation models? So one thing is the unlimited data we can obtain on the internet. So because, as I said, deep learning is good when you have a massive amount of data, when you have enough sufficient data. And one way to obtain this data is we have the whole internet, text or image on internet. And what we need, usually before AI becomes so popular, the one thing limits the data volume is we have to use human beings to label our data. Like if I give you an image, you have to label it as a bird or it's a cat by using human being, which is very intensive, label intensive and expensive. Now, because the people invented unsupervised data, which means we don't have to label our data by a human being. We can label it by itself. For example, one of the most famous unsupervised learning techniques called next token prediction for language models, which means give you a sentence, you ask the model to predict what the next token will be. So in this context, your label is already provided. It's just your next token. So you don't have to label your data by human being. You just ask your label of your sentence. You just shift your window context window to the next to on the right. Then you can get your label. So you don't have to label your data. So your useless unlabeled data in the context of large language models will become something very useful in NLP field. And so what are these transformer? Transformer is an architecture usually contains a decoder and encoder model. So both a decoder and encoder are something like this. So first, your input, first you give your input to a embedding, which essentially convert your text to some number, like which can be recognized by computer or AI system. Then you apply positional encoding to tell the model. Basically, you assign in position index to your data sets, to your token text, to tell model their position relationship. And then you put your input will goes to many layers of attention layer. So one attention layer or transformer layer. One transformer layer is comprised of one multi-head attention layer followed by a feed-forward layer. So feed-forward layer is something I introduced before, just a stack of three linear layers. And this multi-attention layer actually is the most interesting thing, most important thing of your transformer. So before transformer, before attention, how a sequence is processed. So like a recurrent neural network, we have to sequentially process our data. For example, given our data x1, x2, you have to feed your x1 into your model and process output. And because the texts are dependent to each other, for the next token, next text, you have to feed the hidden states of your previous token together with your current step, current text. So you have to do in a sequence way, which is very slow to process. Something like LSTM or some new variant like LSTM, which is also a very old technique, and GRU, they are more efficient to process tokens, sequence data, but still very slow. Until the innovation of attention module, we can actually parallel to deal with your data. What do I mean parallel? Like parallel means you can you can process your data simultaneously without waiting each other. And the limitation of traditional recurrent neural network or LSTM is, even though we can feed the states of your previous text to your next text, it's difficult to maintain every historical information because we will suffer from memory issue. So if the token is far from our current token, their information will be forget. But if we apply attention module as shown in this diagram, a recurrent neural network can only remember short range of your text, and LSTM GRU works better, but attention actually can calculate all the correlation between globally among your text input, which essentially is good because you can actually like you have a bird view of all your textbook. So the transformer essentially contains four parts. So encoder, decoder, and self-attention feed-forward network, which is composed by fully connected layers. And this is the mechanism behind attention. So each input we will calculate for three components of each input called query, k, and the value. So we perform some calculation between q, k, v. With a softmax function, we can calculate the attention scores across different data. For example, if our data is hi, how are you, and we need to calculate the self attention score between different texts. So after the calculation of this attention operation, you can basically have this metric, which means the elements means the correlation between different texts. For example, hi has the largest attention score with itself, and it also, but hi is not very correlated with the rest of the tokens or text. For example, how are you? They are not usually they are not always together. However, how are you or has larger values with each other compared to the hi. So essentially, a soft attention module just tells you how learn the correlation between tokens by itself, so you don't so you can better decide which token or which feature or which token you would like to use when you do make next token prediction. For example, if your current token is how, usually the model will predict R because how and R are usually has better correlation. larger attention than other texts. And after we have know what is transformer, how the transformer model looks like, how can we what's the application or techniques of this model, attention model. So one most famous one is large language models. For example, it's all starts from something like BERT, and within a couple of years, there are so many different large language models developed by different companies. For example, Google gives us from BERT to T5. Now they have Gemini. The picture is somehow is a little bit outdated, so they have Gemini on top of that. And another company is Meta. Meta did a great job by open source their Llama model. And followed by Meta, there are other companies like Cloud. Cloud is developed by Anthropic. Cloud model is here. And Elon Musk's model called Grok is also the current state-of-art model. Also, the DeepSeek. I think DeepSeek is also something we need to mention. DeepSeek, I guess all these credits, most of credits can goes to the open source model of Meta, which called Llama. Once they decided to open source all their code model, then these new companies can build their own technique on top of standing on the shoulder of giants. And for example, I will briefly introduce Llama model, which is still the state-of-art model back to 2023. Now it's somehow lagged behind, but at that moment, Llama 1 model with only 65 billion parameters can outperform ChatGPT, which is 175 billion parameters. And this is Llama 2. The secret sauce of different variants, just you scale your model, you train your model with larger scale data sets with more parameters. This is what they call a scaling law. So once you're training with a bigger model, larger data sets, you will have better performance. And how is Llama was Llama trained is first you're doing pre-training on a massive amount of internet data sets. For example, text, you train with several trillions of text data sets, which is so-called pre-training. After you pre-train your model, you fine-tune a model with some high-quality question answer pairs. Then you also, after you perform fine-tuning, your model will precisely learn how to answer questions, because this pre-training, you basically learn all knowledge on the internet, then you do supervised fine-tuning to learn how to answer, how to extract abstract knowledge to answer concrete questions. And after fine-tuning, you also choose do reinforcement learning with human feedback to align your model's behavior to some human preference. For example, we don't want our model to do some have some safety issue to, for example, to generate some toxic text or image. So we use reinforcement learning to help this. For example, once we found the output has some privacy issue, we use a reward model to penalize your model a bit. Basically, it's slightly changed the weights to align with human preference. This is the 3 steps of training large language models. And after you get your model, you can use your model to do any kind of downstream applications like question answer, text summarization. You can even ask them to write code, to write an article, to generate any kind of videos that associated with your text. This is some statistics of a pre-trained model, pre-trained datasets, how the dataset looks like. And this is the pre-training techniques, what I introduced next, token prediction. And this is how the reward model looks like. It's basically also a transformer. So a transformer is basically dominates every field of current large language models. And there's also some small tiny improvement there and here to improve to make model more easily to train. Use positional encoding. Okay. Now that's it. This is for the talk. Feel free to ask any questions.
Thank you for the nice presentation. Okay. We have some question in the chat. Okay, the first one. Can you see the question? Do you want me to read it?
I can read it. Is
Okay.
activation applied to output obtained from first neurons, make it better before setting it as input to the next neurons? Yes, the activation actually, if you don't apply activation, all the mathematical transformation is linear. So with linear transformation, you cannot approximate different function. Basically, the function in your real life can be nonlinear. It's very complex. Only you use nonlinear activation, you can increase the perplexity of your model. So it's better to apply activation before your output goes to next layer.
Next question.
What is the exact meaning of B? So B is something called bias. So it's a scalar. Will the model learn to end up to your neural values? So it's another parameters. Just you have one dimension to change your output value. What is ReLU? So ReLU is the activation function I introduced before. So it's a type of nonlinear activation function which you applied on your output. Once it's basically it gives you this function. So for all the output that's smaller than smaller than 0, it will gives you 0. For the output bigger than 0, it's just gives you the identity mapping. B is not the error term. B is not the error term. B is basically you can treat it as a parameter. You can learn independent to the weight W. The first B present in is error function.
Just someone want to, I think he answer himself. I hear the term bias.
Yeah.
I'm sure satisfying.
It's a bias. We call it a bias. It's just another parameter you can add it up on your output.
Like you say, the scalar. Yeah.
Scalar. Yeah, this is scalar. Reversed Gaussian graphic.
The remark, maybe it might be interesting. I marked it as a question.
This one?
The relationship.
Yeah, I'm not very familiar with the reversed Gaussian graphic. For me, it's something like feedback learning in control engineering. So you calculate the how do you say residual value between your model output to your label, and then you get some error signal, then you update your weights to reduce the error signal. Where do you get the probability value? I think what you mean is how can we get the probability value of your output for doing prediction classification. So it's before you get your final prediction, you give your output of your final layer to a softmax. So softmax essentially normalize your output between 0 and 1 and make sure their sum is equals to 1. So by doing that, you can get the probability values. Is the combinational neural networks. LMs, most LMs are transformer architecture, and transformer architecture, yes, it's combination of previous networks, combination of feed-forward layer and with the attention block, and many components in transformers like layer normalization, positional encoding, they all developed before in other networks, but it's just independent components you can use in every different type of architectures. So here, most LMs use transformer architecture. Do I rate Luxembourg? Do you consider such a country to banks? I don't think so. I mean, in general, Europe, there, I think Luxembourg it's quite a wealthy country. It has the ability to investigate into AI. And AI doesn't need, like, it's different from traditional industry. It doesn't really rely your size of your country or how many resources you have. You can just investigate chips like GPU. You can use GPU to train your model. And these data sets, it doesn't occupy, it doesn't need place to require to store your data sets. You can store it on cloud. So I think Luxembourg has the potential. It's just how the government's choice, I think. Just like in Europe, I think now France is the leading country of AI because they have a mixture company produce their model. But essentially, I think it's just the government's choice. And Luxembourg is my supervisor actually, Dachmo Mukeno, is a professor in Luxembourg, and he's doing great in sparse neural networks.
Yeah. Yeah, it's true that Luxembourg may be a small country, but its focused investment in research and development have yielded high quality contribution that add significant value to the global community of artificial intelligence. Yeah.
Yeah. At least we have our webinar to promote AI, to educate people. What is the importance of subject to art students? This is a very good question. I mean, we are at the era that like AI will change everything. This is what I believe, which is already, because I'm Chinese. In China, I can say it's already changed. The DeepSeek model already changed many fields. I think for arts, we don't need to learn how to build our model. At least we need to be familiar with how to use our AI to help us to develop things, or to help us to I don't know. For arts, probably people hate AI generated things, but at least we should know what they are doing. How can we adjust ourselves into that field?
Maybe I can say something to that, as my background is in the social studies as well. For if you mean arts in the sense of humanities and arts, then explainability is very important to you, to understand how an AI reasons, what are the limitations of AI-generated data, and where does such data differ from algorithms that are maybe used to summarize information. There's linguistic corpus analysis, for example. This is not based on AI; it's based on algorithms, and there's a big difference. AI can hallucinate, as has been often touched here in the webinars. So it's important for art students, as in humanities and arts, and for social scientists, to understand, to get to know the explainability, the construction and the way that AI can be used and where the limitations are, as to not put out things for facts that an eye might have hallucinated.
Exactly, that's true because 3 years ago at the University of Luxembourg, we launched a project during the event of H22. It's a project, it's about the intersection of artificial intelligence and art, in which we invited artists to learn about the basic concept of artificial intelligence. So we have received artists with proposal in how to enhance their artwork. So we were working together with data science students because the majority of artists doesn't know the technical sides of artificial intelligence. We cannot expect that they will go to the Python programming, but at least they can decide which data they need, which algorithm they can use to enhance their work. If it is a painting, to be designed with a new style, or if it is performance. So we did many projects, many interesting projects that we exhibit during the event, and it was very great, and many people joined looking around the projects, the art project enhanced by artificial intelligence. Yeah, so it's very important that all the topic, including the art, that intersect with artificial intelligence.
The question is, someone who has no background whatsoever in IT or advanced mathematics, they have to admit, I'm having a hard time and start worrying about what's coming at me in the exam. So this is something for Sana and I to respond to, and Amelie.
No worry, yeah, no worry about the exam because we will give a multi-choice question that the answer will be very easy to choose. So it's not a magic thing that we will ask you to do, or a text that we will ask you to write, or a decision that you have to decide. So it just with a few knowledge, if you follow, if you attend the webinar, I'm sure that you will be able to answer the question.
Yes, on top of that, we will have a study guide prepared for you. If you read through that carefully, then you, even if some of the presentations go too far in depth, you would be able to make it with just put some effort into it, and you shouldn't be worried.
Yeah, there is no mathematical equation or any technical equation. Everything is about checking your understanding. That's it.
To this question, yes, to everybody. The Moodle will still be up online even after the last webinar took place, and maybe even after quite some time after the exam took place.
Do we have another question? Okay. Thank you, our speaker, Dr. Chiwi. Thank you so much for your dedication and for the time to prepare the slide and to give us this presentation and to answer the question of our participant. Thank you so much.
No problem, my pleasure. I will share the slides to you afterwards.
Yes, please. Yes, please. Dear participants, I hope that you enjoyed the today webinar. As a reminder, next week is the last one, is about the societal impact of artificial intelligence, ethical, legal, and future consideration in education. The webinar is scheduled at the same time, same day. I encourage you to be active as much as you can. Read the last chapter and post your question about the online chapter in the platform of communication. I will be happy to answer all of them as I usually do. And yeah, the speaker of next week told me that he will try to make the